In this video, let us understand the valuation of Bermudan swaptions. The architecture of modern financial markets is built upon a hierarchy of instruments, from simple assets to complex derivatives. Among the most crucial and widely utilized are those tied to interest rates, which form the bedrock of global finance. Understanding these instruments requires a foundational knowledge of their building blocks, beginning with interest rate swap. An interest rate swap is a fundamental over-the-counter derivative contract in which two counterparties agree to exchange streams of future interest payments over a specified time horizon based on a predetermined notional principal amount. This notional principal is generally not exchanged. It serves purely as the basis for calculating the interest rate payments. The most common structure, often termed a plain vanilla slab, involves the exchange of a fixed interest rate for a floating interest rate. One party, the fixed interest rate payer, makes payments based on the pre-agreed fixed rate. The other party, the floating interest rate payer, makes payments linked to a variable benchmark rate, such as the secured overnight financing rate or the historical London interbank offered rate, which resets at periodic intervals. In practice, only the net difference between these two payment streams is exchanged on each payment date. Building upon the concept of a swap is a swaption or a swap option. A swaption is a derivative that grants its holder the right but not the obligation to enter into a specified interest rate swap at a future date. This optionality introduces a new layer of complexity and strategic utility. The exercise style of the swaption, dictating when this right can be exercised, is a critical feature that defines its character and value. This leads to the taxonomy of three primary types. The first one is European swaption. This is the simplest form where the holder can exercise the option only on a single predefined expiration date. Its valuation is relatively straightforward as it involves forecasting the value of the underlying swap at a single point in the future. The next comes the American swaption. This style offers the most flexibility, allowing the holder to exercise the option on any business day within a given period, up to and including the expiration date. The continuous exercise feature makes it the most valuable and complex to price. The third type is the Bermudan swaption. This instrument represents a hybrid, occupying the middle ground between its European and American counterparts. The holder of a Bermudan swaption can exercise the right to enter the swap on a discrete set of predetermined dates. These dates are typically aligned with the coupon dates of the underlying swap's fixed leg. The name is a market convention, a geographical mnemonic suggesting its characteristics lie between the American and the European styles. The structure of the Bermudan swaption with its discrete decision points is not merely a contractual nuance. It fundamentally shapes the most appropriate valuation methodology. While a continuous exercise right naturally lends itself to a continuous time PDA formulations, the Bermudan's series of distinct sequential choices maps perfectly onto the discrete time-stepping nature of dynamic programming. This inherent alignment makes the Bellman equation backward induction on a numerical lattice the canonical approach for the specific product. Bermudan swaptions are privately negotiated OTC derivatives, allowing for customized terms to meet specific hedging needs. The primary function in the market is to manage the complex risks associated with the embedded options in other, more common financial instruments. The principal application is the hedging of callable bonds. A corporation that issues a callable bond has the right to redeem it from investors before maturity, a right it is likely to exercise if the interest rate falls, allowing it to refinance at a lower cost. This provision represents a liability for the issuer. To hedge this, the issuer can purchase a Bermudan payer swaption. If the rates fall, the issuer calls the bond. It can simultaneously exercise the swaption to enter into a new interest rate swap, where it pays a fixed rate that is now below the original bond's coupon, thus offsetting the financial impact of the call. Similarly, these instruments are vital for managing payment risk in mortgage-based securities. Homeowners typically have the option to prepay their mortgages without penalty, a right they often exercise when the interest rates decline. This prepayment risk represents a significant challenge as it shortens the duration of their interest rate earning assets. To mitigate this, these institutions can purchase Bermudan receiver swaptions. If the rates fall and mortgage payments accelerate, they can exercise the swaption to begin receiving a fixed rate that is now attractively high relative to the new market rates, thereby compensating for the lost interest rate income from the prepaid mortgages. The Bermudan feature can also extend to more complex underlying contracts, such as the cross-currency swaps, which involve the exchange of both principal and interest payments in different currencies. A cross-currency Bermudan swaption introduces an additional layer of complexity, as the exercise duration depends on the joint evolution of both interest rates and foreign exchange rate term structures. These use cases reveal a profound economic function. The Bermudan swaption is thus a cornerstone of risk securitization within the global interest rate markets. The valuation of a European swaption is a relatively straightforward exercise in risk-neutral pricing. One must simply compute the expected value of the underlying swap at a single future point in the time and discount it back to the present. The introduction of early exercise feature in a Bermudan swaption fundamentally transforms this static calculation into a dynamic optimization problem. At each permissible exercise state, the holder of a Bermudan swaption is confronted with a critical decision: exercise the option to enter the underlying swap, thereby terminating the option, or continue to hold the option, preserving the right to exercise at future. This sequence of decisions must be made optimally at each step to maximize the overall value of the instrument. The problem is thus one of stochastic control, where the holder must devise an optimal exercise policy in the face of uncertainty about the future evaluation of interest rates. The optimal exercise decision at any given point hinges on a comparison between two fundamental quantities: the value of exercising immediately versus the value of waiting. The intrinsic value or the excess value is the immediate tangible value that can be realized by exercising the option. It is defined as the net present value of the underlying interest rate swap, calculated based on the prevailing term structure of interest rates at the moment. If the swap's NPV is positive for the option holder, this represents the exercise value. If the NPV is negative, the intrinsic value is zero, as a rational holder would not choose to exercise the option and lock in a loss. Next, we have the continuation or hold value, which represents the value of not exercising. It is the expected value of the swaption at the next exercise state, discounted back to the present, under the crucial assumption that the holder will continue to follow an optimal exercise strategy at all subsequent decision points. The continuation value encapsulates the entire worth of the future optionality, the time value of the derivative. A rational value maximizing holder will adhere to a simple but powerful decision rule: exercise the swaption if and only if the intrinsic value is greater than or equal to the continuation value. This rule forms the basis of the valuation algorithm. From a more formal mathematical standpoint, the early exercise feature gives rise to what is known as a free boundary problem. One can conceptualize the state space of the underlying stochastic factor as being partitioned into two distinct regions at each exercise state. The first region is the exercise region. This is the set of all possible states of interest rate for which the intrinsic value of the swaption meets or exceeds its continuation value. Within this region, immediate exercise is the optimal action. The next is the continuation region, the set of all states for which the continuation value is greater than the intrinsic value. Here, the optimal action is to hold the option and defer the exercise decision. The interface that separates the two regions is the free boundary. The term free signifies that the location of this boundary is not known in advance. It is an endogenous part of the solution that must be determined simultaneously with the options price. This presents a significant mathematical challenge. An elegant physical analogy is the Stefan problem from thermodynamics, which models the melting of ice. The interface between the solid ice and liquid water phases is a free boundary whose position evolves over time according to the dynamics of heat transfer, just as the optimal excess boundary for the swaption evolves according to the dynamics of the interest rate. To solve the sequential decision problem inherent in the pricing of the Bermudan swaption, a robust theoretical framework is required. This is provided by the theory of dynamic programming developed by Richard Bellman in the 1950s. Dynamic programming is a powerful mathematical technique for solving complex optimization problems by decomposing them into a series of simpler nested subproblems. Its applicability extends far beyond finance into fields such as engineering, control theory, operations research, and computer science. The foundation of this method is Bellman's principle of optimality. The principle asserts that an optimal policy must have the property that, regardless of the initial state and the initial decision taken, the remaining sequence of decisions must continue an optimal policy for the subproblem that starts from the state resulting from the first decision. In simpler terms, any part of the optimal part is itself optimal. This principle allows one to solve a complex multi-period problem by starting at the end and working backward, solving a simple one-period problem at each step. This step-by-step recursive procedure is known as backward induction. The principle of optimality gives rise to a recursive equation known as the Bellman equation, which formally relates the value of a problem at one stage to its value at the next stage. For the Bermudan swaption, this equation precisely captures the option's excitation. Let V of t, RT represent the value of Bermudan swaption at time t, given that the state of the world is characterized by short-term interest rate RT. Let the set of permissible exercise states be T1, T2, T3, and so on till Tn is equals to capital T. The Bellman equation provides a recursive relationship for the value function V at any exercise date Ti, which is given by V of Ti, Rti is equals to max of exercise value of Ti, RTI, continuation value of Ti, RTI, where exercise value is the intrinsic value, that is the net PV of the underlying swap if exercised at time Ti, given the rate RTI. And the continuation value is the value of holding the option. It's the risk neutral conditional expectation of the discounted value of the option at the next exercise date, Ti plus 1. Given all the information available at Ti, mathematically this is expressed as the expected value under the risk neutral measure of e to the power of negative of integral from Ti to Ti plus 1 RSDS times V into Ti plus 1, RTI plus 1, given the filtration Ft, where the filtration denotes the information available at time Ti. This recursive structure is the key to solving the problem. At the final exercise state Tn, the continuation value is 0, so the options value is simply its intrinsic value. Knowing the value function at Tn, one can use the Bellman equation to compute the continuation value at Tn minus 1. And thus, the full option value V of Tn minus 1, Rtn minus 1. This process is repeated, stepping backward in time from one exercise day to the previous one, until the value at time 0 is determined. This is the essence of the backward induction algorithm. With this, let's conclude the part 1 of Bermudan Swaption pricing. In the next part, we'll look into the Hull-White model and constructing the Hull-White trinomial tree and implementation of the backward induction algorithm, with also an implementation in Python.